Okay, welcome to Chapter 3, Atomic Structure. So we've already talked a little bit about the brief history of chemistry and the atom concept from way back in the ancient world. Now we've jumped ahead. We've skipped over a lot of history that we'll pick back up when we talk about gas laws and such. But the reason for jumping to atomic structure now is it's important from early on in the course to understand why elements behave the way they do, why elements form the compounds that they form. And this all has to do with what's happening at the atomic level, the electronic transitions and the ways electrons are transferred or shared. Our learning objectives for this chapter, we're going to explain the electrical properties of an atom and describe how the properties of electricity explain the structure of atoms. There'll be some experimentation that we'll talk about and how that led to the discovery of X-rays and an explanation of radioactivity. And then we'll distinguish the three main kinds of radioactivity: alpha, beta, and gamma decay. Additional learning objectives include being able to sketch the nuclear model of the atom and identify the key parts. We'll also be listing the particles that make up the nucleus of an atom and give their relative masses and electric charges, if any. Identify elements and isotopes from their nuclear particles, so be able to tell based on number of protons, for instance, what element we have, and then the isotopes are distinguished when you have the same proton count by various neutron counts. We'll define what a quantum is, and then we'll be able to arrange the electrons in a given atom in energy levels, which we'll call shells. In addition to those learning objectives so far, we'll also relate the idea of the quantum of energy to an orbital within an atom. We'll be able to write an electron configuration using subshell notation for a given atom. And we'll be able to describe how an atom's electron configuration relates to its location in the periodic table. So why do these elements that are in a vertical relationship on the table tend to behave in a similar fashion? It obviously will have to do with this electron configuration. Alright, and then finally we'll be able to distinguish the conversion of solar energy into electrical energy in a solar cell from the conversion of solar energy into the chemical bond energy of a solar fuel. And last but not least, explain why splitting water into the elements hydrogen and oxygen requires an energy input, and why producing water by the reaction of hydrogen and oxygen releases energy. Okay, so we'll get that idea of going one way will cost energy and going the opposite way will release energy based on the dynamics of the particular reaction under consideration. Alright, so thinking about electricity in the atom, we'll have to define a few terms before we can get too far along here. So first and foremost, let's talk about what an electrolyte is. A lot of sports drinks and other beverages on the market today tout the electrolyte content. An electrolyte generically is a compound that conducts electricity when it's in the molten state or when it's dissolved in water. And obviously it's the dissolved in water case that the Gatorade and other Powerade such beverages for sports, they're really looking at potassium and sodium contents, but really any compound that dissolves and conducts electricity in water would be considered an electrolyte. In addition to electrolytes, we'll also define electrodes, and here we'll talk about electrodes as either carbon rods or metallic strips that carry electrical current. So those shouldn't be in your sports drinks. Hopefully you don't find any in any that you've had to drink. Alright, so electrolysis is a process whereby we use electrical energy to cause a chemical reaction to occur, and in electrolysis we'll need to talk about anodes and cathodes. So the anode is the positively charged electrode, and the cathode is the negatively charged electrode in an electrolysis setup. And as you can see in our little diagram, we have the negative cathode being the site where the electrons are being forced by that outside electricity source, and that's causing the cations down in the solution, those positively charged ions, to be attracted to that end and to gain electrons. On the reverse side, you have the electrons being pulled from that side, creating a partial positive charge there on the anode, and that causes the anions, the negatively charged ions in the solution, to be attracted to the anode and to give up electrons. So talking about anions and cations, we've sort of skipped ahead here. So let's just define ions in general. An ion is an atom or a group of atoms with a full positive or full negative charge. So the atom, in this case, has either gained additional electrons from its neutral atom state or lost electrons, one or more electrons, from its neutral state. So if it happens to gain one or more electrons, we call it an anion, a negatively charged ion. If it's given up one or more electrons from its neutral state, then we call it a cation, a positively charged ion. We see here in this example now a Crookes tube, an example of a cathode ray tube from the mid-1800s. And so a cathode ray is really a stream of electrons. And if you are more than maybe 20 some years old, you probably remember the old cathode ray tube televisions. Many of us older folks grew up with those really thick TVs, very heavy cathode ray tube televisions that didn't have great resolution, not like the thin flat panel plasmas, not so much anymore, but mostly LCD and LED displays. Well, these cathode ray tubes relied on a high voltage source to generate the stream of electrons, and they were, at being negatively charged, they were repelled from a negative plate and attracted to a positive plate, and so the cathode ray could be directed to a specific region. And obviously this attraction and repulsion figures in prominently into the behavior of not only electrons and atoms, but also some of those particles we'll talk about when we talk about nuclear decay. So using a cathode ray tube, J.J. Thomson, Joseph John Thomson in 1897, was able to determine the mass-to-charge ratio of cathode rays, and finding that they were indeed massive particles, he was able to discover the electron. So electrons haven't been known as such for very long in terms of history, but an important discovery back in the late 1800s. Interesting note, Thomson's son in the early 1900s actually was given the Nobel Prize for proving that electrons have wave characteristics. So the father discovered electrons as particles and won the Nobel Prize, and then the son showed the wave characteristics of electrons and won another Nobel Prize. But again, you can see in the experiment that it's the same sort of cathode ray tube setup, and showing that the cathode ray tube was generated by negatively charged cathode rays that are truly particles known as electrons. All right, now we back up a few years to the 1886 Goldstein experiment, which showed there were, in addition to the negatively charged cathode rays, there could also be observed some positively charged rays when the cathode was perforated. So they would be going in the opposite direction, and they would be traveling more slowly than the electrons, and it was found that the particular particles generated depended on the identity of the gas that was used in the discharge tube. So the lightest gas that was used, hydrogen, was used to show that these light particles, the positively charged particles, were not nearly as light as the negatively charged electrons. They were about 1837 times the mass of the electron, and this is where we end up eventually with the discovery of the proton. Okay, so fast forward back to 1909 here. We're with Robert Millikan in the famous oil drop experiment. And if you remember, J.J. Thomson was able to determine the mass-to-charge ratio of the electron after he proved its particle nature. Well, here Millikan, through his painstaking oil drop experiment was able to determine the charge, and therefore, since the mass-to-charge ratio was known, also the mass of the electron. So we see the schematic. You have the atomizer to get very fine droplets of oil, not individual atoms. Atomizers don't make things into individual atoms, so don't get confused by that name, but it does make very small droplets. And then as the droplets fall through the positively charged plate and down to the negatively charged plate through some ionizing radiation, Millikan was able to relate that rate at which they fall and the mass of the particles to the charge of the electron. So some very painstaking work that eventually gained Robert Millikan fame as the first person to determine the charge and therefore also the mass of the electron. Okay, so after all that emphasis on electron particles and positively charged particles, we have also around the same time, the late 1800s, 1895, Wilhelm Röntgen discovered X-rays. X-rays are not particles, they're light, very, very high energy, short wavelength light that Röntgen was able to discover using a cathode ray tube. The electrons emitted by the cathode ray tube were able to knock out core electrons from certain metals, and then as new electrons fell down to replace those, they released X-rays, very high energy electromagnetic radiation. And so obviously, since the discovery of X-rays, not only have we had the medical applications like the medical X-ray of the hand here that we see on our right, but you also have X-ray diffraction, which is a very important method for determining the structure of solids. So crystalline solids are able to have their crystal structures determined based on the interaction with X-rays. So probably the medical applications are well known by those of you taking the course, but maybe the importance of the X-ray discovery to chemistry in terms of solid state chemistry may be less known, but very, very important to our understanding of structure today. So a lot going on there in these late 1800s, right? We also have in 1895, in addition to Röntgen discovering X-rays, we have Antoine Becquerel discovering radioactivity. So he noticed that substances, minerals that he had stored in a drawer were able to cause a photographic plate to develop. And so that he wasn't sure what that was. He thought maybe they had absorbed light energy from the sun, and this was what was causing the development. But even samples that had never been exposed to the sun were causing the same thing, and so he was noticing that there's something going on. And for the next decade and a half, we have Marie and Pierre Curie working together side by side in an old greenhouse on their university campus to isolate pure radioactive substances. And obviously Marie Curie, very famous woman in science, her dissertation was probably the most important dissertation ever published, noting multiple new elements, and she eventually died of cancer. Radiation caused cancer likely, but I think that if you asked her today, she'd probably say it was worth it. So important discoveries. Pierre was killed in a horse cart accident, but Marie lived quite a bit longer and did quite a bit more work in the area of chemistry and physics. All right, so we see here in our graphic three of the main types of radioactive decay that were discovered early on. The radioactive material itself is housed in a lead block. That's to keep it from interacting with the discoverer, the observer, and to force it only through one direction, through the hole in the center front of that block of lead. There's a negatively charged plate and a positively charged plate just before the photographic plate, and as you see, the alpha particle is slightly deflected toward the negatively charged plate, so therefore we understood that it must be a positively charged particle. The gamma particle goes straight through. It's neither attracted to the positive nor the negative plate. And finally, the beta particle has a large deflection toward the positive plate. So the beta particle must therefore be negative. And comparing the alpha and the beta deflection, the alpha particle it must be much more massive than the beta particle, which explains why the alpha particle does not have much of a deflection toward that negative plate, whereas the beta particle has a large deflection toward the positive plate. So now, after much painstaking work to get exact amounts, the table here, table 3.1, shows the names alpha, beta, and gamma, which we had the Greek symbols for on the previous slide by the Greek letter, alpha, beta, and gamma, as we saw previously. Now the masses in terms of atomic mass units, the alpha particle has a mass of 4, the beta particle 1/1837th, and the gamma particle, which is not a particle at all, but a gamma ray, therefore has a mass of 0. It's light energy, it's not a particle in nature, so it's essentially massless. If we look over at the charge, the alpha particle has a 2+ charge, and as we'll learn in a moment, the alpha particle is actually the nucleus of a helium atom. So it's the helium nucleus minus those 2 electrons in the outside of the atom. Therefore, it has a 2+ charge rather than being a neutral helium atom. The beta particle is an electron, and it has a -1 charge. And again, it's much lighter than a proton, 1/1837th the mass of a proton. And the gamma ray has no mass and no charge, which is why it went straight through, was not attracted to either the positive or negative plate in the previous example. All right, so still in the 1900s now, 1911, Ernest Rutherford publishes his famous paper detailing his gold foil experiment. And so we see an apparatus in the graphic below that shows the discovery of the nucleus. So Rutherford didn't set out to discover the nucleus. At the time, Thomson, who had discovered the electron, gave us a plum pudding model of the atom, where the electrons were just sort of distributed throughout, and you had the nuclei, the denser, more massive parts like plums in the pudding, where they just randomly occurred. So Rutherford was designing an experiment to show that, to verify Thomson's plum pudding model, but instead the gold foil experiment radically changed our understanding of atomic structure. So you had an alpha source, and again, alpha radiation being helium nuclei. They're very, very massive. So he's shooting these massive particles through a very, very thin layer of gold foil, probably just several atoms thick, really, by the end of pounding it to that thin sheet. And so what he would have expected would be that all that alpha radiation goes through, and that's what happened. But instead of just having it all go through, there were a few alpha particles that were deflected at varying degrees, and some were coming almost right back at the alpha source. And this meant that there must be a very dense nucleus that accounts for the bulk of the mass of the atom, and his analogy to what his findings was, it was like shooting a missile at a piece of paper and having it bounce back. That's how unexpected these results were, and how radically the Rutherford gold foil experiment changed our understanding of atomic structure. So now we have the nuclear atom. We have the bulk of the mass in that positively charged nucleus, and the bulk of the electron itself being empty space. The atom itself being empty space with the electrons outside in that empty space. All right, so again, just showing that idea of almost all of the alpha radiation goes through, but some is deflected either because it hits a nucleus at a glancing angle and then it just gets deflected, or hits it almost dead on and it gets sent almost straight back. So the main ideas that we have is it's not anymore a plum pudding model. It's not just protons and electrons distributed through each other, but rather a situation where the atom is made up of mostly empty space and very, very small, massive nuclei in the center, and light electrons outside the center of the atom. So an important first step toward understanding the nuclear atom, but again, as we'll see, the modern idea of the atom is changed a little bit from what Rutherford and Niels Bohr, another important name in the nuclear atom had initially found. All right, so we see here in table 3.2 the various subatomic particles, at least the level we'll go to in this fundamental chemistry class. Obviously, you can get much smaller in leptons and quarks and all of that if you want to go into particle physics, but here in fundamental chemistry we talk about the three subatomic particles, the proton, the neutron, and the electron, and we leave it at that. The proton is the positively charged, so its symbol is a lowercase p with a plus sign. The mass is 1 atomic mass unit, essentially, and then the charge is a +1, and it's right in that dense nucleus, and it gives the atom its identity. So proton count is what determines the element that you're dealing with. If you have just 1 proton in the nucleus, then you're hydrogen. If you have 2, now you're helium, and so on and so forth. Sometimes an alternate symbol is just a hydrogen atom because it's mainly a proton. So hydrogen +1 actually would be the proton with the electron missing. But we'll stick with our book that says P+ is the standard symbol. For the neutron, the standard symbol is lowercase n. It has a mass roughly that of the proton. Again, if you go into particle physics, you're going to find that the neutron's a little more massive than the proton, but for our purposes, a mass of 1 atomic mass unit, just like the proton, is good enough. It being neutral, the neutron has 0 charge, and it's also in that nucleus. So the nucleus is where the bulk, the overwhelming majority of mass is, and that mass is due to the protons and neutrons, if any. Most elements have at least 1 neutron. Hydrogen, in its most common isotope, has just the proton. Finally, we have the electron with the symbol lowercase e-, and its mass is very, very small. Sometimes it's given essentially a mass of 0, but here our text says it's 1/1837th the mass of a proton, as we saw back in the experiment where the positive particles were found and measured. That's where we got that 1837 ratio for the hydrogen plus that was making it through the perforated cathodes. And the charge of the electron is a -1, so it's equal in magnitude but opposite in charge to the proton. Protons are +1, electrons are -1, and it resides outside the nucleus and gives the atom its volume, although most of its empty space. The electrons define the volume of the atom. Alright, so now that we have a good sense of the atomic structure, a dense, highly positively charged nucleus with negatively charged electrons around it, we can go a little deeper into the ideas of what determines the element identity and the isotope identity of the element under consideration. So first we'll have to talk about atomic number, and that's the number of protons in the nucleus, and that gives us the particular element that we're considering. So if, as I said before, if we're element number 1, atomic number 1, meaning 1 proton in the nucleus, we're hydrogen. If we're atomic number 3, 3 protons in the nucleus, we're lithium, and so on and so forth. The mass number now gives the sum of protons and neutrons in the nucleus, and this will help us with the idea of isotopes that we'll talk about in just a moment. Alright, so an isotope is a substance that has the same atomic number but different mass numbers. So meaning we're the same element, which therefore means we must have the same number of protons in the nucleus, but we have a different number of neutrons. Again, the neutrons don't have any charge to them, they just contribute additional mass, so they won't change our atomic number, but they will change our mass number depending on the amount of protons and neutrons that are present. So here, if we consider just 1 proton, that gives us the element hydrogen. Hydrogen comes in 3 varieties. The overwhelming majority of hydrogen atoms are what we call protium, just 1 proton in the nucleus, no neutrons, mass number of 1, just like an atomic number of 1. Then if we look in the middle of our graphic, we now have 1 proton and 1 neutron, so our atomic number stays 1, we're still hydrogen, But now our mass number goes up to 2 because we have the 1 AMU from the proton and 1 AMU from the neutron, and now we're dealing with deuterium. It's still hydrogen, that's just the name of the particular isotope that has the neutron as well, sometimes known as heavy hydrogen, and deuterium is the isotope used in heavy water nuclear reactors. Finally, if we have another neutron added to the nucleus, still just one proton, so we're still hydrogen, but now we have tritium, which is a radioactive isotope of hydrogen. So we don't have as much stability once we start adding additional neutrons in this case. If we were to try to add a third neutron, we don't have a stable enough atom anymore, and I don't think that there's been a case where you have a hydrogen atom that's been able to be stabilized with the 1 proton and 3 neutrons. So we just have the protium, the most stable and most abundant type with no neutrons, just the 1 proton, deuterium, 1 proton and 1 neutron, and then tritium, 1 proton and 2 neutrons. So now that we're getting to the stage where we know an awful lot about these atoms and we can even distinguish isotopes, we need to have a standard way of writing the atom and its particular isotope if we're considering isotopes. So the way we do that as chemists is using the nuclear symbol, and so we have the element symbol, which is noted here as X, A usually up to the superscript before the element symbol would be the mass number. So if we were dealing with hydrogen as protium, for instance, that mass number would be 1. If we were talking about hydrogen as deuterium, that number would be 2. And hydrogen as tritium, that number would be 3. The subscript there right before the element symbol would be, for protium, it would be 1. For deuterium, it would be 1. And for tritium, it would be 1, because each of those would be examples of a hydrogen isotope. So Z, the atomic number, depends only on the identity of the element, and it's the same for all isotopes of an element, but the mass number A would change. There are other ways that you might also see it written, like hydrogen-2 is another way that we can distinguish deuterium from protium, which would be hydrogen-1. But this is the standard, and this is the way we would expect to see it in our chemistry class. I mentioned Niels Bohr a few slides ago as an important follower from the Rutherford nuclear atom. The Bohr model of the atom gives us sort of a planetary model where you have the dense nucleus sort of as the sun and the electrons orbiting like planets in our solar system. It breaks down at a certain extent, but it gives us a pretty easy to follow model. And if you think about the flame tests, different elements give different colors to a flame. This is due to the different characteristic transitions. So if we think about a sodium atom, for instance, as having its nucleus be the sun in a solar system type arrangement, you'd have different transitions going between the different levels. And when the flame test gives enough energy to make those transitions happen, as they fall back down, the preferred transitions give the characteristic color to the flame. So sodium gets that sort of yellowish color because of its key transitions of electrons from their excited state by being in the flame back down to their ground state, their regular state. And you'd have for potassium, the element below sodium, you'd have a characteristic color that's more of a lavender. So depending on the particular element nuclear planetary model, you'd have different size transitions and therefore different wavelengths of energy emitted as electrons fall back down from their excited state to the ground state. So if we go back to Aristotle's idea of continuous matter, we would expect a continuous spectrum to arise from that sort of a model of matter. Of course, we don't get that, as we saw on the previous slide. We get discrete transitions, preferred transitions, which go along with our discrete atomized idea of matter. So again, that continuous spectrum, you would think about white light going through a prism, for instance, and being separated into a continuous spectrum of all the visible colors of light. In the case of atomic transitions, you don't get that because it's not a continuous type of matter. It's a discrete matter, and it displays discrete matter behavior by showing just select transitions, preferred colors, because only certain transitions, planetary type jumps, are allowed. You can't jump any amount you want. You have to jump and fall back down in certain quantized amounts, localized amounts, depending on the identity of the element that's getting its electrons energized and then having them fall back down. So here we see an example of some of these line spectra. So line spectra arise from the gaseous element having its light pass through the prism, producing a key characteristic spectrum. If you see up top is the continuous spectrum that we might expect from continuous matter if matter existed that way. Instead, we get bright line spectra that are characteristic of the elements. So you see cadmium there has a few lines in the visible. Again, of course, there are lines in the ultraviolet that we can't show here because we can't see that as human beings. But depending on the element, you get a characteristic pattern, almost a fingerprint, if you want to think about it that way. And you have to be careful when we analyze light from outer space. Sometimes we're able to get an idea of the elements that are present. We only get one spectrum, and we've got to realize it's probably multiple elements laid upon one another. But if you can get a good idea of what's out there in places far too far away to visit, that's how we know things like the composition of the sun. It's hydrogen, helium largely, and various other solar bodies, stars and other planetary bodies. We can analyze the light or elements by line spectra. All right, so back to Bohr's atom, and I used the idea of a quantum, a quantized amount, when I talked about discrete matter. A quantum is a tiny unit of energy produced or absorbed when an electron makes a transition from one energy level to another. So if we look here for the hydrogen atom, you have multiple possible levels. So n equals 1 would be the ground state. That's the place we'd expect the electrons to be in a non-energized hydrogen atom. If we're going to stick that hydrogen sample into a discharge tube and pump it full of energy, then we're likely to cause those electrons to be promoted to upper levels, unfilled levels in the ground state, but now filled levels, and that requires a certain amount of energy. So if we look, pumping the energy from n equals 1 to n equals 2 is a very large amount of energy. So we don't get any visible wavelengths. We get ultraviolet wavelengths because of the large energy needed to do that. And so it takes a lot of energy to pump it up, and the energy is emitted as it falls back down. The transitions back down to n equals 2 for hydrogen are the ones that are in the visible range. So if you have an electron falling from n equals 5 down to n equals 2, that's going to be a violet colored wavelength. If it's falling from n equals 4 down to n equals 2, it's going to be a green color. And if it's falling from n equals 3 to n equals 2, it's the shortest transition, so therefore the longest wavelength of light, which would be in the red region. So all of these characteristic transitions give rise to those visible line spectra, and you'd see, if you're like most of us, you'd see 3 bright lines. There's also a fourth that's down a little more in toward the violet, ultraviolet region that some people can see. That would be n equals 6 falling down to n equals 2. Alright, so taking a moment to step back and define some of the terms that I've already been using fairly loosely. When electrons are in their lowest energy state, which again at room temperature most of the atoms are at most of the time, they're said to be in the ground state. Okay, so the ground state is the lowest possible energy situation for all the electrons. If energy is put into the system from a flame or electricity source or some other sort of voltage scenario where the electrons in the atom absorb energy, now those ground state electrons, or at least some of them anyway, are promoted to a higher energy state. So we would say that those electrons are now in an excited state. So an excited state is unstable, which means the electrons will fall back down to the ground state, And so when it returns to that lower energy state, the way it releases that energy is as a photon, a little packet of energy, a light particle, if you want to think about that. If we get into the Einsteinian duality of light, very quantum physics that probably few, if any of you, have studied in any detail, myself included, that photon would be observable as light. Now, for us as humans, we can see in the visible spectrum, and some of those photons would be visible, but many of them might be higher in energy, the ultraviolet region, for instance, or even X-rays, as we talked about. If you have a very highly excited electron, or an electron that falls back down to a low energy orbital, then X-rays are emitted, and that's one way that X-rays were first discovered, was by the relaxation of excited electrons back down to a low ground state. Now, in the Bohr-style atom, we had these energy levels or states, sometimes referred to as shells. Nowadays, we call them principal energy levels, but in the older terminology, they were referred to as shells. And so for the simplest atoms like hydrogen and helium, you only had electrons in the first shell for the ground state. Once you go into the next period on the table, starting with lithium, now you've started to fill the second shell, and so on and so forth, up through the end of the table. So the smaller the atom, the fewer electrons it has. In the ground state, the fewer shells that are occupied. So we've talked about the Bohr model because the Bohr model is fairly easy to understand. It's sort of like the solar system, with the nucleus being the sun and then the electrons orbiting around these planets. But that's not quite the case. And so the model of the atom that's accepted today, the quantum model, is a probability-based model. So it's no longer clearly defined orbits like in the planet and sun analogy. Instead, it's orbitals, which are regions of probability of finding electrons. So 95% of the time, for instance, you might find the electron in this orbital. So now the language is shifted from shells to principal energy level, and then sublevels and orbitals to describe this probability model, the quantum model of the atom. So it's much less defined. It's a little more abstract, tougher to get our minds wrapped around, but unfortunately it's closer to the actual reality of nature. So it would be nice if the Bohr model, an easy model like that, explained all the behavior, but it does not. Once we talk about quantum mechanics, then we have to talk about the quantum model of the atom. So if we want to map our language for the quantum model of the atom back to the older Bohr atom, what was called by the Bohr atom model as shells, these are now principal energy levels. And so they're most nearly the distance that an electron is from the nucleus. So the higher the principal energy level, the further the electron is from the atom's nucleus, and therefore the higher the energy of that electron. If we look at sublevels, these were known as subshells in the Bohr model, and now in the quantum mechanical model, we have each principal energy level being divided into the same number of sublevels. So for instance, if we look at the hydrogen and helium atoms, they're in principal energy level number 1, so they'd have one type of sublevel, which we'll come to know as an S type orbital. If we go to the next period, period 2, starting with lithium, now we have principal energy level 2, we'd have 2 sublevels, and what we'll come to know as the S and the P sublevel. So every time we go up in a principal energy level, we gain a new type of sublevel. The orbitals themselves are those regions in space that represent a high probability of locating an electron. Again, it's a probability. There's some chance the electron could be somewhere else, but the highest probability would be to find it within that orbital. And each of those sublevels has one or more orbital types. So in principal energy level 1, where you only have the 1s sublevel, you'd have just one type of orbital, which would be a spherical type of orbital. And then when we go into principal energy level 2, now we have 2 sublevels, and we still have the s, the spherical shaped orbitals, or at least one of them, the 2s orbital, but we'd also have 3 of these 2p orbitals, which are more lobe-shaped. So here we see that probability distribution with the s orbital on top having a roughly spherical arrangement of the probabilities and having some chance of finding that electron at the nucleus. If we look below, the p-type orbital has a node at the nucleus, so you can find the electron. There's a chance of finding the electron in a lobe shape on either side of the nucleus, but there's a node, there's a 0 probability of finding that type of electron right at the nucleus. And so the earliest ideas about atoms, that they were treated like hard spheres, well, that holds pretty well, even with this sophisticated probability-based quantum model of the atom. We see the s orbital is spherical, so a hard sphere makes sense. And then we see the 3 p-type orbitals, the px, the py, and the pz. When we combine all of these from the second energy level, the s and p orbital types, we get something that, again, fills roughly a spherical shape. So treating atoms as spheres works really well. Even with our more elaborate understanding, they still tend to behave in a spherical type of arrangement. So now that we hopefully have a better sense of how those electrons are laid out in three-dimensional space, it's convenient to be able to represent this as shorthand notation. So instead of drawing these orbitals as probability distributions, it's convenient to be able to write what are known as electron configurations. So as it says, that these configurations allow us to represent the arrangements of the electrons in an atom. So we'd have the principal energy level indicated, in this case 1. Principal energy level 1 is the one we're talking about here. We would indicate the sublevel, and here the electrons are in an s-type sublevel, which is the only sublevel in principal energy level 1. And then finally, we can have up to 2 electrons in each orbital. So in this s orbital, we happen to have both electrons filling it, and therefore we have the electron configuration of 1s2, which would be the ground state electron configuration for the helium atom. Now moving up to a greater number of electrons, if we look at nitrogen, which is element number 7, it has 7 protons in its nucleus, and in its neutral ground state atom it has 7 electrons in those lowest energy orbitals. And so we have the first main level, the sublevel s, the 1s filled with 2 electrons. Then we move up, nitrogen being a period 2 element, we have the second s level, sublevel also filled, 2s2. And then we have the p sublevel. Now that we're in principal energy level 2, we have 2 sublevels, right? The number of the principal energy level also tells us the number of possible sublevels. And so in order to get our total of 7 electrons, we've used up 4, 2 in the 1s and then 2 more in the 2s. And now finally we have 3 electrons left for the 2p sublevel. So the nitrogen example might be a little misleading because things get more complicated once we get up beyond the second sublevel, the second principal energy level, into principal energy level number 3. So as you see, we have the filling order, and if you just follow the arrows, first we fill the 1s, then we fill the 2s, then we fill the 2p. That's what we saw with the nitrogen example. And then we move into the 3s just like we'd expect, and we fill the 3p. But when we get into that the 3p and 4s levels, things get a little complicated because the energies become very, very close. And actually, you might expect that we would fill the 3s, 3p, and then 3d, but that's not what happens. We fill the 4s before we fill the 3d. And then we go back and fill the 4p and the 5s, and then we go back down to the d's. So what you'll notice is the d sublevel is always filled in the principal energy level 1 higher. So we don't fill the 3d until we've started to fill the principal energy level 4, filling that 4s. Likewise, we don't fill the f's until 2 periods later. So we wouldn't fill the 4f, for instance, as you can see in the diagram, until after filling the 6s. So just be careful. The s's and the p's are always the principal energy level indicates the level of the s and p orbitals that are being filled in what's known as the valence, the outermost electron shell. But for periods 3 and above, we don't necessarily fill every sublevel. We stop at the 3p and then move up to 4s and back down to 3d, and similar things with the f's, that 4f's aren't filled until after the 6s. So things get complicated when we get those d and f sublevels, and we'll notice on the periodic table the d and the f sublevels have special locations in the table because of that peculiarity of filling order. And we see here the electron configurations for the ground state of the atoms of the first 20 elements. So nothing unusual. These are all what we call the main group. And so they exist in either the first 2 columns or the last 6 columns on the periodic table. That's where we tend to find our main group elements. In the middle, we get the transition elements, and then down below, we get the lanthanide and actinide series, the rare earths, so to speak. But these 20 elements are very predictable. Their chemistry, if any, helium and neon, for instance, don't do any chemistry because they're very, very stable. We'll come to know that group 8 or 18 as the noble gases because of their limited chemical reactivity. But the ones that do chemistry have very predictable chemistry because of their regular electron configurations. So you notice in these first 20 elements, we fill the s's, and then if we're in principal energy level 2, we fill the p's, principal energy level 3, we fill the s's and the p's, and then we move up to the 4s's. We haven't filled any of the 3d sublevel in the first 20 elements. It's not until element 21 that we start to fill the d sublevel. So these first 20 elements, which you should know by name and symbol, have very regular, very predictable chemistry because of their electron configurations. So the periodic table, Mendeleev's huge contribution to chemistry, is the most predictive tool in all of chemistry, or at least many of us chemists would agree on that. It's because of the layout in the table that we can predict the type of chemical behavior of those elements. Things that are in the same column in the periodic table have the same ending electron configuration. For instance, if you were looking at the previous slide, sodium and potassium and lithium, they all ended NS1. So whatever the principal energy level was, whether it was 2 for lithium or 3 for sodium or 4 for potassium, that last electron in the ground state was either in a 2s1 orbital for lithium, a 3s1 orbital for sodium, or a 4s1 orbital for potassium, and therefore they all tend to have similar chemical reactivities in that same group. I skipped hydrogen for a reason, and we keep it separate, but the rest of that NS1 arrangement, electron configuration, again, has very reliable chemistries. So the vertical columns are called groups or families. That would be group 1 for the what's known as the alkali metals, the lithium, sodium, potassium, etc. The horizontal rows are the periods, and that's what differs. So the periods have to do with distance from the nucleus. So potassium being furthest, having its outermost electron furthest from the nucleus for those examples, would be the most reactive, whereas lithium, which had the lowest principal energy level of those three, would have the least reactivity because the electron would be closest to the nucleus in that case. All right, so a little more about those groups and families. So the vertical columns in the periodic table, as I mentioned, the group 1 there are the alkali metals. They're a family. They have similarities, similar chemical properties. If we go to the very end of the main table, group 8 or 18, the noble gases, they have limited chemical reactivity. Way up at the top, like helium, for instance, ends in a 1s2, and that's a very stable configuration. All the other noble gases end in ns2, np6, because you've got the S and P sublevels to worry about. So neon starts us with that, and then going down, they all end in the N, whatever principal energy level it is, S2 and NP6. So we expect similar chemical properties. Notice that it's not always as you go down a family that you get more reactive. If we look at the group 7A or 17, just to the left of the noble gases, they're more reactive as you go up because of the chemistry they do. In the case of the alkali metals, it was losing electrons, so the further the electron was from the nucleus, the more reactive. So potassium was more reactive than sodium. For the group 7 or 7A or 17, the halogens, they're more reactive as you go up because they're gaining electrons, so it's easier to gain that electron if you're close to the nucleus, like fluorine, compared with being far from the nucleus like iodine. So reactivity depends on the type of chemistry that happens. Periods, as we said, there's a horizontal rows in the periodic table, and the elements of the period demonstrate a range of properties from being very metallic, like those alkali metals, sodium, potassium, lithium on the far left, to being non-metallic noble gases all the way on the right, or the halogens on the group, the family just next to the noble gases, just to the left. So those would both be examples of non-metallic families compared with the metals, which tend to occur further left in the table. So as we've already mentioned, the chemistry tends to be those outermost electrons, what are known as the valence electrons, that define the chemistry of the elements. So they're the electrons in the outermost principal energy level of an atom, and for what we call the main group, those first 2 columns and the last 6 columns, ignoring for at least a little while the transition elements, those 10 columns in the middle, and then the 14 columns set down below the table of lanthanides and actinides. For the main group, it's usually an NS whatever, NP whatever. So those are the electrons that are gained, lost, or shared in a chemical reaction. The metals tend to do the losing, so the leftmost elements on the table within a period would have their valence electrons lost until they get to a stable electron configuration, one like the noble gas that precedes them. The nonmetals tend to gain electrons, so they tend to gain enough electrons to get them to the noble gas configuration that follows them. And then the elements that are in the middle, like carbon or silicon, in that group 4 in particular, they do a lot of sharing. But group 3 and group 5 can also be involved in sharing, especially as we move down in the periodic table. The elements in a group or a family have the same number of valence electrons, so we expect them to have similar chemistries, but things do differ. For instance, if you think about carbon, carbon combines with oxygen to make carbon dioxide, which is an odorless, colorless gas. If we go down 1 in the periodic table, now you've got silicon. Silicon dioxide's a very hard substance, solid at room temperature and pressure, that we commonly know as sand. So even though we expect similar chemistry between carbon and silicon, since they're in the same family, they don't always do quite the same thing. So we do have differences as well. Just like within any family, there are similarities and differences. Okay, so back to our example families, and again, the electron configurations. The same groups in the periodic table have special names, and so that group 1 that all ends in NS1 aside from hydrogen, which is our 1s1, and it's different, it's a gas at room temperature and pressure, so we exclude it from the remainder of group 1 or 1a. The rest are all metals, and we called them the alkali metals already, and the reason they all have similar chemistries is they all end in NS1. So lithium would end in 2s1 for its valence electron. Sodium would be 3s1, potassium would be 4s1, so on and so forth down the table. Right next door, group 2 or group 2a would all have the valence electron configuration ns2, and just like we left hydrogen out of the group 1a, we leave helium out of group 2a. It doesn't fit, it's a noble gas, it belongs with group 8a or group 18 rather than 2a or group 2. Because if we start with beryllium, we have 2s2, and then magnesium is 3s2, and calcium 4s2, and so on and so forth. And they tend to be much more similar to each other than helium. The halogens, that group before the noble gases, that's group 7a or group 17, depending on the table you're looking at. And they all have the valence electron configuration ns2, np5. So our first halogen is fluorine, 2s2, 2p5. And then as we move to chlorine, 3s2, 3p5, and bromine, 4s2, 4p5, and iodine, 5s2, 5p5, so on and so forth down that family of halogens. They tend to be very reactive because they're just missing one electron from the noble gas. So if they're able to gain an electron from another atom, then they can have that stable configuration and become a -1 ion, just like the alkali metals in group 1 tend to lose one electron to become +1 ions, and the alkaline earth metals tend to lose 2 electrons to become +2 ions. Finally, the group 8a or group 18 that we already discussed, those are the noble gases, and they tend to do very little chemistry because they have the very stable valence electron configuration ns2, np6. Again, helium is just 1s2. There's no p sublevel in helium, but starting with neon, we have 2s2, 2p6 on down the road. Some of the larger ones at the bottom of the noble gases, those elements have been forced into reaction with reactive elements like fluorine or oxygen, but the smallest members, helium and neon, still have not been forced into any chemical reactions, even under extreme conditions. So in addition to the chemical similarities we would expect between the different types, metals, nonmetals, and metalloids, we get some physical properties. So chemically, metals tend to lose electrons to become positively charged ions. Nonmetals tend to gain electrons to become negatively charged ions, and metalloids tend to do a lot of sharing. Well, for physical properties, the metals tend to have similar physical properties. They tend to have metallic luster. They tend to be good conductors of heat and electricity. They tend to be malleable, which means you can pound them into thin sheets, like Rutherford did with his gold foil for his gold foil experiment. And they tend to be ductile, which means they can be drawn into wires, like copper wiring for electronics. So good examples would be sodium and copper. But again, about 2/3 of the elements, most of the periodic table, would fall into the class of metals. Nonmetals tend to have a dull luster. They tend to be non-conductors of heat and electricity, or at least very poor conductors of those things. And they tend to be brittle in the solid state, so you can't pound them into thin sheets very well. And some examples are sulfur and bromine. Sulfur, a yellow powder, and bromine, a reddish liquid at room temperature and pressure. And then finally, the metalloids tend to have sort of in-between properties. They demonstrate properties of both metals and nonmetals, or properties of neither in some cases. And some examples would be silicon, which is a semiconductor and basis of the electronics industry, silicon computer chips. And also arsenic would be another example of a metalloid. And the metalloid tends to be that staircase that divides the metals and the nonmetals in the periodic table. So here we see a periodic table in terms of filling, orbital filling. Doesn't show period 1, but it's starting with the 2s sublevel, and then the 2p, and then the 3s and the 3p, and then finally the 3d, which, as we've already said, comes after the 4s in terms of ground state filling order, then the 4p, 5s, then we're back down to the 4d, and then 5p, 6s, and then finally we get to the first F sublevel, which happened back in principal energy level 4, but we don't start filling it in the ground state until after the 6s sublevel. Then we go back and fill the 5Ds and then the 6Ps, and now we're up into 7S and 5F and 6D. And then we pretty much get to the end of our table that we know today. There's some in the 6P sublevel that have been discovered since this schematic was made. But again, those filling types and the types of orbitals or sublevels that are being filled really define the types of elements that we're dealing with. So the NS1 tends to be the alkaline metals. The NS2 would be the alkaline earth. And then as we skip over to group 3A or group 13, now we're filling NP1, and then NP2, 3, 4, 5, 6. And then now finally we're filling the Ds, the transition metals. So we're filling the ND 1 through 10, and although there are some exceptions there in the ground state that don't quite go 1 through 10, but we'll save those for a later discussion. And then finally the 4Fs, which 4F and 5F filled F1 through F14 in this sublevel type. Okay, so the main group of the table again is the S's and P sublevels, then the transition metals, those 10 elements that typically appear in between, and then finally those inner transition metals tend to be offset down below the table for most modern periodic table layouts. So as we've tried to do in the other chapters, our text likes to look at some green chemistry examples in each chapter, and here we're looking at solar fuels. So sunlight is an abundant source of energy, and one that's we've done a better job of trying to capture in solar cells in recent days. But plants have been at this for quite some time, and so plants have become masters of storing solar energy as chemical energy via photosynthesis. So we see here photosynthesis, carbon dioxide plus water plus sunlight yields carbohydrate plus oxygen. So this is the way that plants store that sunlight, which in a true chemical reaction we wouldn't put as a reactant. The sunlight would be shown typically above that arrow, but the sunlight is captured, at least some of the energy from that is captured to chemically rearrange the carbon dioxide and water into carbohydrate and oxygen. And that's how plants generate oxygen that then we're able to use as aerobic respirating organisms. The artificial photosynthesis that we've been most successful with so far is trying to generate hydrogen fuel, still using water, only instead of using carbon dioxide, we're just breaking that water down directly, capturing the light energy to separate water chemically into hydrogen and oxygen gas. Once the hydrogen and oxygen gases are generated, typically it's the hydrogen gas that we're after, because that hydrogen fuel can be reacted with oxygen again to produce heat and electricity. And the reason for this, solar cells are wonderful, and solar energy has been subsidized so that people will go green, go solar. But in Binghamton, in the summer, it works really well. In the winter, not so much. We don't have as many hours of daylight, and the winters when we really need a lot of that energy. So being able to save the energy, store that solar energy as hydrogen, means we have a usable form of energy. That hydrogen fuel can be used at night when the sun's not shining, or in the wintertime when the sun doesn't shine very much at all in our particular region of the country. So hopefully you've had a good experience here with Chapter 3. There's a lot in here. It's a very dense chapter, but it explains a lot of the behavior of the atoms and the sorts of chemistry that these atoms will be doing that we'll be talking about for the rest of the semester.